So this is, us getting in our time machine and going back in time to, the very beginnings of chapter 2. We're just trying to cover our bases for some of the things that we didn't study way back then. And one of them is this alternative definition of the derivative. Okay, so this definition right here presented is one that we learned at the beginning of chapter 2 that propelled us in, to finding derivatives, where we take a secant line, right? That is, let's see, this yellow line right here is our secant line, right, to the pink function between points P and Q. And then we shrink this distance, right, of h. We shrink that down to nothing, right? We take the limit where Q gets insanely close to P, and then we end up with a tangent line. Okay, so what we have in this next drawing is kind of same idea, just different notation. So this is obviously, let's not be in yellow for so long. This here is the difference quotient, right? AKA slope, right? This is just y2 minus y1 over x2 minus x1 with a limit, like above, thrown into it. So this drawing here represents the same idea. This is a secant line through these 2 points, okay? And instead of calling the distance here, right, x minus a, instead of calling that h like they do up above in that drawing, right, we're just letting it literally be x minus a. And instead of saying h approaches 0, we're saying let x approach the value a, so that those points get really close together, and we end up with a tangent line as well. Okay, so these again are both, what the derivative equals, okay, when we work them out. So if we read along here, right, both definitions present the same idea and simply utilize different notation. The idea is that we start with the slope of a secant line to a function, and we let the distance between the 2 points that create that secant line shrink down to virtually nothing, thus creating the slope of a tangent line, right, which is what we've been obsessed with in chapter 2. So this definition here, right, this row is your original definitions. Okay, the calculations that we're making next are dependent on, am I getting a function for my answer or am I getting a number for my answer? So you'll see the difference between the 2 columns is that you have a c value in place of x, right, in this row. And then in the bottom row, we're using the alternative definition, and there we have a c value. You can put it in place of x or you can put it in place of a. It really doesn't matter. Oh no, this is missing its limit definition. So stuck right here should be the limit as x approaches c. Okay, so I'll make sure to include that when I get this out to you guys. So we're going to be making calculations both based on what, the format of the function. We have to pick out what is f, and then we may or may not have to plug in a number. Okay, so in number 1 here, right, this is formatted like the original definition, because I know that because it says h approaching 0, right? So h approaches 0, that means I'm just supposed to figure out, right, this is f of x, whatever comes after the minus sign, I'm just supposed to figure out what f prime is, right? So since f of x is x to the 1/2 power, f prime of x is 1/2, oh boy, 1/2 x to the negative 1/2. Okay, that's it. That's my answer, right? I'm just trying to take the derivative. That's what that particular problem is asking me to do. Okay, if you wanted to write it in its, radical form, cool, you can do that. In the next one, right, this is the x approaching a, right? I notice it's totally different based on what I read underneath the limit request, right? So that means in this particular case, right, as noted, look up above, highlight in this f of x appears first in this definition. So I'm going to make the same calculation, right? F of x is x to the 1/3, and this particular limit will just calculate the derivative of that. So 1/3 x to the negative 2/3, right? And that's fine as is. Okay. Now, parts 3 and 4, examples 3 and 4 here are much different. because we actually have, well, 3, we have constants in here. So you'll notice, right, I have 8 plugged in all over the place, and I'm letting x approach 8. So that means, right, this is modeled after x approaching c of f of x minus f of c over x minus c. So my job is to take the derivative and plug in 8. That's my task, okay? Actually, I shouldn't say take, I should just say find f prime. And then step 2 is plug in 8. So in this format of the definition, my function appears first. So first thing I'm going to do is establish that f prime of x is 2/3 x to the negative 1/3, which, you know, is 2 over 3 cube root of x. And then my second step, right, is to plug in 8 to that. So I write f prime of 8 like a that, and take the cube root. So I get 2 over 3 times 2, which is 1/3. Okay. 4 is much like number 1. I'm going to let you try that one on your own. The other one I'm going to do with you is number 6 here, so you get a taste of what it's like when we plug in a constant to the original definition. So referring up here, right, I'm back to this one. That's the format that I'm looking at. That means my job is to find f prime of x, and part 2 is to plug in negative 3. You know, because h is approaching 0 here, I know I'm not plugging in 0 because that's not the format, right? The format in this case for finding c is to pull c, not from the limit statement, but to pull c from the actual, you know, work that we're taking the limit of, that negative 3. Okay, so step 1, my function must be x squared. I can tell that because that's what comes after the minus sign, and even though there's a negative 3 there, that's in place of x. Okay, so once I establish that, the derivative is 2x, and then step 2 is to plug in negative 3, which is 2 times negative 3, which is negative 6. Okay, so sometimes we end up with functions, right, like we did in 1 and 2, just the derivatives themselves. And then sometimes, you know, when the problem has c values plugged in, we actually plug in the c value and we come up with numerical answers.